Thank you very much. Thanks a lot for inviting me. So my name is Krenn. I'm a research group leader at the Max Planck Institute for Science and Life. And I'm not a philosopher, that's very important to appreciate my talk. I'm a quantum physicist. And actually, I decided to not talk about so much about our work on understanding with AI, but I would like to first start with a real case study of a discovery that we made with AI. I will go through it. And then instead of you asking me questions, I will ask you some questions. So, but in order to appreciate that, I need to introduce a little bit of quantum mechanics knowledge. So, Robin already said you're not convinced by quantum mechanics.
No, I'm thinking about what it says about reality.
Oh.
So I think I would have a nice chat with your former boss.
Mm-hmm. Yes, very likely. Okay, good. So we'll go exactly into this direction.
Nice.
So who knows about quantum mechanics? Okay. Okay. That's very good. So who knows about quantum entanglement?
About what?
About what? Quantum entanglement. Perfect. So then consider this as a light refresher. Right. In my research group, we are investigating AI that can make conceptual contributions in science. And we do this mainly in two directions. The first direction is using AI for designing new quantum experiments. And from those experiments, we can learn new concepts and ideas. That will be the example. The second case, we use huge amount of scientific literature and try to predict and hopefully suggest new interesting research directions. But I will mainly focus on the first thing, and after I ask you some questions, if there's still some time, I will go then into a more big picture where I show you more examples of how AI can be used in science practically. Okay, so the question about this AI for designing new experiments and quantum experiments started during my PhD. So I was working with Martin Seilinger in Vienna, and he is very much interested in quantum entanglement and quantum correlation, exactly the picture that Florian mentioned about what does it mean about our world. And usually the group wants to see those phenomena actually in the lab and play with them and test them. So what is quantum entanglement? The simplest form of entanglement is, imagine you have two photons, and those two photons, they can have colors. So imagine those photons can be red or they can be green. If they are entangled, they can be in a superposition between red and green, which means that before you measure them, they don't have a well-defined color, and only when you measure them, then when you measure the first particle and you see it's red, then you know the other one is also red. The curious thing is now, those two particles can be as far away as you want. There are experiments that show this phenomenon over 1,000 of kilometers between satellites and ground stations. So this is the simplest form of entanglement, and this type of entanglement has been investigated since the early 70s, and 1 year ago, the Nobel Prize in Physics was given for those pioneering experiments. But the goal of Seilinger's group and that of my PhD was to go further, investigate more complex types of entanglement and try to understand more about it. So a more complex form of entanglement is, instead of having two particles, you can now have three particles. Where all three particles can now either be red or green. And again, the same thing, before you measure them, they don't have a very different color. And when you measure the first one, you see its color, and at that moment, the others also have that well-defined color. So multi-particle entanglement, by the photon entanglement in that case, is basically the resource for quantum computers. So they are extremely important, and people try to create huge entangled quantum states now. So those states have been investigated since the late 1990s or early 2000s. A different way you increase the complexity of entanglement is by adding more colors. So now you have two particles, and those two particles can be either both red, or both green, or both blue. Okay, before you measure them, and so on. So this is called dimensionality of entanglement. So here, the dimensionality of this entanglement would be 3. So those two particles are 3-dimensional entanglement. In this case, you can communicate the individual photons carry more than 1 bit of information per photon. That means when you increase the number of dimensions, you can increase the number of information per photon, which is very interesting for communication tasks. Therefore, those type of entanglement is very interesting for quantum communication tasks, and also studied roughly since the early 2000s. But at the time of my PhD, we wanted to go further and investigate what happens when you have systems that are high-dimensional multi-particle entangled at the same time. The simplest case is this: you have 3 particles now, where all of the 3 particles are red, or green, or blue. And again, before you measure them, they don't have well-defined colors when you measure them. All particles take the well-defined color. And this was a state that during my PhD has never been created in the laboratory. So no one was able to measure the properties of those states. And not only experimentally, it was never produced, even theoretically, there were a number of open questions about this type of quantum state. And therefore, we wanted to create it and observe some of its property for the first time in the laboratory. So usually, what happens when you want to create a quantum state, or you want to build an experimental setup in this research field, you put a blackboard or you put a piece of paper, and you write a little bit. And usually you find a suitable experimental configuration rather quickly. But for this state, it was quite different. So we tried, which means me and my colleagues, 5 people involved, we tried for several hours. We couldn't find a solution. And we tried for days and for weeks, and we still couldn't find a way how we can produce the state in the laboratory. So there was no way how, that we can observe its properties in the lab, because we cannot even produce it. So then after a few weeks, I thought maybe the human way of designing experiments is not necessarily the best one. And I thought about maybe automizing the whole process of designing an experiment, which just our intuition is our way. And then I wrote a simple computer algorithm. Step 1. Right. Yeah. What's that one? Sorry?
Where we see it on the screen.
You see it on the screen?
Blue.
Closer. Yes. Okay. Yeah, you click on the mouse.
Yeah, it's the big.
Do you see the mouse?
Yeah.
Perfect. Yeah. Okay, then we'll do it. So the idea of the algorithm was very simple. We start with an experimental toolbox, which contains all optical elements that we have in our laboratory. This could be lasers, beam splitter, crystals, and so on. And from there, the algorithm is allowed to take those elements and start randomly arranging it on a virtual optical table. Then it starts to compute its properties, and if the property is such that it fulfills the criteria that we want to have, it reports it to the user, and everyone is happy. But in addition, it is trying to simplify what it found and adds the simplification to its own toolbox. And in that way, for the next iteration, it can already use those macro components that it already found out that are useful, can use them already and start from there. And this is a discrete learning step that is increase the speed of the algorithm by several orders of magnitude. So to create more complex setups, you don't have to start from scratch anymore, but you can already use what you have found to be useful. So I wrote this algorithm, and after in the evening I started it, and in the morning I came back and I saw a solution.txt file at my desk. And we looked into the solution.txt file, and it was indeed an experimental setup that none of us have thought about, and that solves exactly the problem that we were not able to solve for several weeks. And this solution was then actually practically implementable. It only took roughly 3.5 years to put this computer, this kind of solution, then at the optical bench and observe for the first time this type of quantum correlation. So we were obviously very happy about this algorithm and tried to apply to other questions we were not able to solve by hand. We found new ways to control photonic systems, single particle systems, multi-particle systems, new ways how to measure photonic systems. And recently we also applied it to the generation of certain quantum states in other type of quantum computers, for instance, here in the IBM superconducting quantum computer. So this was great, but for me what was even more interesting is that we were able to learn new ideas with this algorithm. And that worked in the following. So after we were searching for this high-dimensional multi-particle entangled state, I took my algorithm and put it on a few free computers in the lab, and let it search for a much more diverse set of quantum states. So if you think about it, when you have three particles, those three particles can be correlated in an asymmetric way. For instance, you can ask the question, how is particle 1 correlated with particle 2 in this entangled state? Or how is particle 1 correlated with particle 3? Or how is particle 2 correlated with particle 3? So for 3 photons, you get 3 different answers now about what is the complexity of entanglement. And I can show you an example here. So this is the state that I showed in the very beginning, the first 3 particle entangled state. Who could guess what this 3 numbers is for this state? Any guess? Okay, I show you the answer first. So here in this case, the first particle can take 2 numbers. That means it is 2-dimensionally entangled with the rest of the state. The second particle also, the third also. That means those 3 questions all have the same answer because it's a perfectly symmetric state. Therefore, this number, which is called Schmidt-Rank vector, doesn't matter so much, is 2, 2, 2. Let's go to a more complex state. What are the 3 numbers here?
All perfect correlation?
Yes?
3? Yes, please.
Yes, right. So 3, 3, 3. Perfect. And now, a more difficult example. What about this state? So, each of the colors represent a different number. 2. Second?
1, 2, 3, 2.
Okay, you only have 3 numbers. 1 number per particle.
Okay.
1, 2, 1, 2, and
So you have 3 numbers. The first number represents how many degrees of freedom or colors does the first particle have? 42. Yes. Perfect. Who was that? Very good. Okay, so quantum physicists. Very good. So now we have this much more general way to think about entanglement when you have more particles and more dimensions. So I let my program try to find experimental setups for these type of states. Okay, so when it has those when those three numbers are well defined. And I start in the following way. So here I start with two photon pair creations. That means in total I create 4 particles, and then my algorithm creates the experimental setup. And if it's one of those well-defined triplets of numbers, then it is a state that I'm interested in. And now, as a computational constraint, I let those crystals produce 3-dimensional entanglement. So the whole resource that this setup can use now is 2 times 3-dimensional entanglement. So at that point, I had the point in mind, and I knew that this algorithm cannot overcome the bound of 9. So we'll never find any experimental setup that can produce more than 9-dimensional entanglement, because just the resources are not here. So I thought that must be physically limited. So, but when I run now my algorithm for several weeks, and I came back to it, I saw that it found one solution that seemed to overcome my bound. So this solution overcame this bound of 9 dimension because it is 10-dimensional entanglement. I thought, okay, there's definitely a bug in the program. So I was very worried that all of the other results are also wrong. But I checked and it worked out. So the program actually produced an experiment that can create 10-dimensional entanglement. And at that point, I was obviously super curious what is going on. So I was looking into the solution. And this was the solution. And I have absolutely no idea what it means. So there is something that can overcome the bound of entanglement, which I derive from all of my physics knowledge. And I completely don't understand why. So I looked at this for hours and for days and tried to understand how is it possible that it overcomes this limit. And then after several days of looking at it, I saw that what it does actually is it uses an idea that was invented basically in the early 1990s for a completely different reason in quantum physics. And it uses this idea and combines it with this modern question of quantum entanglement. And as soon as I saw this, I was able to kind of extract a concept. I was able to extract this idea and was able to generalize it to many other cases. So now, with this outlier, basically, we were able to create many, many new experimental setups that for which we don't need the computer anymore to search for it. So, and we were extremely happy about this, and we described this theoretical idea in a PRL paper. PRL is one of the leading journals in physics. So we wrote this paper, and we're very happy we described the idea that was discovered in a way by a computer. Just a little bit later, it turns out we didn't really understand what the computer was trying to tell us. We found that one of the statements, one of the generalizations that we had was actually wrong. We had to add an atom, which is not so good. But we tried to understand why this is wrong. And actually the reason why it was wrong is because we thought about it in a way too simple way. And actually the correct way to think about it showed us a connection that was not wrong between quantum physics and graph theory. So then after we found this mistake of the interpretation of what the computer did, we found this hidden link between quantum experiments and graph theory. We then wrote several papers in the following few years about this link to graph theory and quantum physics. And it led to new interpretations of quantum interference, of computation, and so on. And recently, some of the most efficient algorithms for designing new quantum experiments are actually based exactly on this principle of on this link between quark theory and quantum physics. And not only these new AI methods can use this link. There are many experiments that now are built that actually explore exactly this link between quark theory and quantum physics. So these are 3 experiments, all of them published this year. So now my questions to you. How would you describe this situation? Who discovered this link first, this new way to think about quantum entanglement? And second, this new way to think about this quark theory connection, which we only found because we didn't understand the first interpretation well enough. Second, who was creative in this process? Was someone creative? Yeah. So these are my questions to you now.
I shall point at people and tell you to answer. That is not fair. Lena, you if you like to say.
Yeah, sure. So thanks first of all. I think it's really cool, and to me, it's kind of an illustration of Alex. Actually, the point you made about my talk, like the AI becoming a tool in the lab and being used like as a tool and something that provides some concepts itself. Who discovered these ideas? Well, good question. I would say the one who put the machine into motion then, but maybe other people think differently.
What if this whole thing would be just one huge for loop? Huge for loop. One huge loop which is entirely uncreative from the industry.
What?
One like brute force is just going through this entire space.
Yeah, but isn't that also what we see in like discovery processes where many humans are involved all of the time? Somebody has an idea, they bounce it to somebody else, they ping it back with some new inspiration. So, and then it's also like, actually, this is the question about patterns oftentimes, like, who created it anyway?
Yes.
Who is going to get like the reward?
Yes.
Huge question. Thanks.
Thanks.
Inspiring.
I know we've got some thoughts, but Adrian, you haven't said anything yet.
Yeah, so I think one of the key things here, it feels like, is that you're able to translate it from kind of this kind of messy real world thing into just maths. And once it's just in maths, it is entirely an optimization problem in this mathematical framework, from what I understand. And this kind of method of solving that is a very efficient way of solving that optimization problem. And as you're saying, you could have written this as just a for loop that tries every possible combination in increasing length or whatever. And this is arguably what people are kind of doing by hand when they do it. So in that sense, I'm saying you're just like replacing doing by hand with doing it on a computer, but you've added some really useful efficiency gains so this actually works, right? So from that sense, I'll say it's the creator of the program. It's not the program
So
itself.
2 times for the creator already? No, okay.
The person who wrote in and corrected your PRL.
She became then co-author of one of the following. Things, obviously. Yes. Okay.
Oh, I saw.
Sorry, you go.
No, sorry,
You can.
I saw Eamon next.
You
and
did.
then 2 certain.
But I see.
Oh, right.
So I was thinking maybe in these scenarios, if we try to think about this concept from a multidimensional lens, like the questions become a bit more clear, because when you ask who discovered these ideas, you are asking those who hear, your audience, to pick one person. But if we say who discovered this aspect of the idea, like the interpretive aspect or optimization aspect, then it feels like we have more options to answer the question. Similar thing you can say about the other question, like who was creative again, who was creative about the optimization procedure, machine, who was creative about interpretation, like human. And then we get like a richer, like kind of like perspective or language to explain what is happening in this discovery creation process.
That's why I like the philosophical question and you criticize the question. What is this kind
What's creativity?
Well, yes, I can answer that question. But no, wait, Amy,
No, mine really was handled, yeah.
oh, you really, okay.
Yeah, maybe just throwing some thoughts there. I mean, maybe you could say that the algorithm helped you distill certain things that were implicit in the setup that you already put in there, right? And in writing the optimization program in a certain way. And on the last question, that's actually a question that philosophers have addressed big time. For instance, a very famous paper by John Searle, he said like, well, you could imagine if I execute a program, you could also imagine me sitting in a room, getting Chinese symbols, having a manual, and then spitting out Chinese symbols according to that manual. It would look like I was speaking Chinese, but I would not comprehend anything. And then he goes through all the iterations while the room understands. Well, it's also maybe possible. Okay, so deep learning is maybe a bit different, or complex machine learning, but it's like you have like this a stack of books, then you pick one, doesn't work well, get electric shock, and get to the next book. So this is basically the optimization that goes on in deep learning, right? You have like a stock of functions, you take one, try whether it works, no, it doesn't work, you give it a little shock and it gets the next one. So it's still in the same sense, if you think that's not understanding, then this would also not be the machine understanding, but it can do something that's as good as understanding. That's what I would say. I would say like it's not the same thing as whatever that is. We don't have a hard time saying what that is exactly. I would say there's some grounding in consciousness maybe or so, and that's clearly missing, I suppose, in algorithms. But if you agree that this is a good argument to think the machine is not really understanding, you could say, well, still it can emulate understanding. It can do something that's, for many purposes, pretty much equivalent to that. Maybe that's a good framing for that. I don't know.
I'm a bit, Mike, you have something to say, and I might say something.
Sure, yeah. So building on what Atusa said, if you want to specify what's discovered, then that helps us. And I think you do this red circle helps us. So who discovered that? And then I think the answer would be, like, suppose you made this algorithm, it did all this stuff, produced exactly this data. You looked at it for a while and you said, no, and you sort of didn't catch on that there was this interesting possibility. And then, you know, a grad student somewhere later on picked it up and they said, actually, this is super interesting. And then they went on with it. I think it would probably be them, we would say, who made the discovery, even though you had done this previous stuff. So I think like there's got to be some interpretation of something as a solution to a meaningful problem. Involved.
The interesting thing for me was, because that was the first case, several times later, that was the first case, this principle idea that we used there was in the solution. So it completely implicitly used this idea that we afterwards extracted. So it was already inside there, but implicit. Yeah.
I'm gonna use my privilege to say what I think. Look, so some of us around here think that it's possible for groups to know things as a group that individual members don't themselves know. Warren expressed skepticism about this view, but it's a view that has been gaining some credibility, and you know, I think the best version of that view is consistent with there being different individuals knowing different parts of a whole, but they're interacting in such a way that the group whole knows that whole. Now, we'd be focusing on things like belief and knowledge, but then there's an interesting question about, first of all, what is part of this collective? Is it just people? Or could be people and things? And I thought that's why I was hoping anyone would say something, Steve, you might say this sort of thing. But there's no reason why I'd say, well, it can't be and the program. So this team, it's a combination of people and things or software.
Yeah, that's not obvious.
And then if you grant this, then there are going to be interesting questions that aren't properly explored, but yet are beginning to be explored. Well, group knowledge, can it be group understanding? Is that somehow different? Group imagination, interesting idea. Can we, as a group, imagine things that we aren't individually imagining, which would be relevant to the question of whether there can be creativity ascribed to this group as well. So I'm just saying that there's a whole bunch of research that might answer these questions in a way of not picking out individuals, but saying it's the group, and that the group might be not just people, but people and things or that sort of stuff.
It's a very good
Hey, sorry to interrupt. Things that finger.
It's finger.
Yeah, and then I think cluster and then.
So actually, I think this idea about knowledge or creativity or understanding or whatever we have been distributed is actually something that's also familiar in the philosophy of science about explanation, for instance. There is the idea that, you know, explanatory knowledge can be distributed across the scientific community where different experts zoom into a system in different ways because they're utilizing different methods, so they gain different insights. So I actually find it quite attractive.
I like that. Last you were next to my mental map and then.
Thank you for the great, for sharing this great example. And I completely agree with this school perspective. And it's a very nice illustration of it because also the reviewer pointed out to something or someone from the community and the kind of.
Was exchange student who came, I gave this one day later, she said that must be wrong. It's very embarrassing.
But it is this idea that we speak about that the science is a collective endeavor and everybody plays their role. And what I find interesting in this question is, so some people would say that AI could be like extending our human cognition, or, I mean, for me, what's interesting there is what's the difference between a microscope with which we can just see more, and what's the difference between using algorithms to learn and whether they really add something like what you were trying to describe here, that like really open our perspectives, add some epistemic diversity to the whole process. I think that's an interesting case.
Thanks.
Yeah, coming back to these questions and Alexander's answer to that, I think also it is, to me, it's quite obvious that this Excel sheet alone that you're having there is not a discovery in and of itself. But it takes someone to do the heavy lifting, the interpretation of what that means, and what it means to the rest of the body of theory, to make it a discovery. That doesn't start there, but it also began when you, I don't know, first started programming your program there. So although this was a very helpful tool, it still involved humans, in this case you, to make the heavy lifting, to make it actually usable theory, or yeah.
Yes, that's Mary, please.
Yeah, I just wanted to add, I really liked your way of seeing it, and I was exactly thinking about microscopes and telescopes, you know, the role of this interaction that we have. And often we say, you know, these tools give us prosthetic perception. And this seems like it gives you prosthetic imagination because you can just explore possibilities that were not previously available. But it's just one very specific part of the process of the creative process. You still went in at the start and the beginning to evaluate. So it's involved in a very specific part of the creative process. So I'm thinking whether we should introduce this term of prosthetic imagination. Does this make any sense? I like the sound of it though. Yeah, super exciting stuff.
Now, did you want to ask? Go on. Yeah.
So the account of applied maths generally that I've been developing, I've been calling it conceptual prosthesis. I think it's the same thing that you're getting at. I mean, I think the use of ML in these ways is sort of that on steroids, but I think all math kind of works like it extends our reasoning ability about phenomena that enables us to have thoughts about something that we wouldn't otherwise be able to have without the representation in form.
It's a miracle.
That too. ML is extra miracle.
We'll go on for a couple of minutes. Kathleen, you haven't said anything on the topic, and
yeah, so just to maybe not let ourselves off the hook so easily, I think the way that you set this up is very nice, right? And I'm sure it's intentional in that both number one and number two involve this thing that we think of as being archetypally creative, right? This idea of arbitrage, where you take some result from the 90s or from graph theory, and you bring it into this area where it hadn't previously been applied. In the first case, you know, implicitly you think that the system is doing that. In the second case, your new collaborator is doing that. So I think we have to acknowledge there's a parallel intellectual activity here or activity that's being performed of something that we often describe as being creative. And I think we should grapple with that. So yeah, I do want to push back on the idea that this could be creative.
So positive, right?
In a positive way, and say that, yeah. Against the rising tide of, no, it's just a tool, blah, blah, blah.
Okay. Thanks. I like it.
Lena, when you have the last, or perhaps penultimate word in case of time, so Adam.
I actually have a quick question to you. When you said it only took us 3 years, were you being serious?
Yeah,
Like that this is short for putting this into a physical setup?
Yes, totally serious. Previously, we had to develop new technology, which we knew already, because no one has investigated multi-particle and high-dimensional entanglements at the same time. So we knew already, starting this project, we need to develop new technology, which I didn't know which one. And then my tool showed which one. And yeah, it turned out to be several years. We expected it. So that is not something very, very uncommon.
So our laughing was a bit out of place there. We should have applauded.
Applauding is,
Yeah.
applauding is entirely appropriate, so let's,